Microwave antennas, problems on dish and lens antennas, series on antennas and wave propagation, lecture number 5.20. Here, right now, in the present session, we consider some problems and also their solutions. Problems being set on dish antennas and lens antennas. These problems are mainly concerned with their gain, beam width, and effective apertures. Let us move further and begin the session. Consider a problem example 1. The aperture diameter of a 1.43 GHz dish antenna is 64 meters. Find its first null beam width and also its power gain with respect to isotropic radiator and then with respect to a half wave dipole. This problem is set on dish antennas. Solution. Given that antenna is working at 1.43 GHz, wavelength corresponding to this frequency is 0.21 meters. This can be obtained by considering C to F ratio. C is wave velocity, F is wave frequency. First null beam width is approximately double of half power beam width. This is a general relation connecting first null beam width with the half power beam widths. It applies to dish antennas too, so we can use it here. So first null beam width is 2 into 70 lambda by d. This 70 lambda by d is half power beam width of dish antenna. Lambda is available, d aperture dia is available 64. Using the available values of lambda and d, one can determine FNBW. In the present case, it is 0.46 degrees. Notice it is not even 1 degree, less than half degree. So the beam is very narrow. Dish antennas are associated with narrow beams. Power gain of dish antenna is given by the formula 6 d by lambda square. This formula. Using the values of d and lambda, one can find G as 557.2 into 10 power 3. Notice this is a huge number. Dish antennas are associated with huge amounts of gain. Another observation. In dB, with respect to isotropic radiator, it is 10 log 557.2 into 10 power 3. Apply 10 log to this absolute value of gain, then we will be getting gain in dB, dBi. The gain with respect to that of half wave dipole is 557.2 into 10 power 3 by 1.64. 1.64 is gain of half wave dipole. This ratio gives the value of dish antenna gain with respect to the gain of half wave dipole in absolute terms. If we want it in dB, then we have to apply 10 log to this quantity. Another problem, example 2. A 10 cm radar uses a 5 meter parabolic reflector and radiates pulses of 20 kilowatt. What is the effective pulse radiated power? This is the problem. This is also on dish antennas. Solution. First, we have to find out power gain. It is 6 multiplied by d by lambda square. D is 5, lambda is 10 cm, 0.1 meter. Using the given values, G can be obtained. In the present case, it turned out to be 1500. This is power gain of the antenna. Now the effective pulse radiated power is, we are asked to find out this particular quantity. It is product of pulse radiated power with power gain of the antenna. Gain of the antenna is 1500. Radiated pulse power is given as 20 kilowatt. Multiplying these two, we will be getting 300 into 10 power 3 kilowatts. This is the answer. Another problem, example 3. Calculate first null beam width of a 2-meter dish antenna used at 6 GHz. Also compute the gain and effective radiated power of this antenna when its total radiated power is 2 kilowatt. Solution. We are asked to find out first null beam width. We are also asked to find gain and effective radiated power. For their calculation, we need wavelength. The wavelength corresponding to 6 GHz is 0.05 meters. First null beam width is approximately double of half power beam width. We know it well. So first null beam width is 2 times half power beam width, which is 70 lambda by d for dish antenna. Substituting values of lambda and d, we will be getting first null beam width as 3.5 degrees. Then we move to power gain. Power gain is given by the formula 6 times d over lambda square. Substituting the available values for d and lambda, one can get g easily. In the present case, it turned out to be 9600. Effective radiated power is product of power gain with total radiated power. Total radiated power is 2 kilowatt. Gain is 9600. Therefore, effective radiated power becomes 9600 into 2 kilowatts. It becomes 19.2 into 10 power 3 kilowatts. This problem is also, one can see, is on dish antennas. Another problem, example 4. Find the directivity of a 460 millimeter circular parabolic dish functioning at 12.5 GHz, assuming an aperture efficiency of 75%. This problem is about finding directivity. Solution. Radius of aperture. Directivity is diameter is 460. The radius becomes 460 by 2 equal to 230 mm. This is radius. Physical aperture area then is pi r square, pi into 23 square in square centimeters. Then effective aperture. Effective aperture is aperture efficiency multiplied by physical aperture. It gives 0.75. It is aperture efficiency into pi into 23 square. This is physical area. So effective aperture is available. Wavelength corresponding to 12.5 gigahertz. It can be found. In the present case, it is calculated here. Lambda turns out to be 2.4 cm. Now directivity. Directivity is equal to 4 pi over lambda square into AE. This is standard formula. To find directivity from this formula, effective aperture is required, lambda wavelength is required. We have already calculated both these quantities. Substituting the values in the expression, we get directivity as 2722. Another problem on dish antennas. Example 5. For a 3 GHz dish antenna, half power beam width is equal to 2 degrees. Determine beam solid angle, directivity and effective area. So frequency is given, half power beam width is given. We are asked to find beam solid angle, directivity, effective area. How to get them? Let us see. Solution. Given that theta hp equal to phi hp equal to 2 degrees. In radians, it is 0.035 radians. What is theta hp? It is half power beam width in vertical plane. What is 5 HP? It is half power beam width in azimuthal plane or horizontal plane. Dish antenna usually gives symmetrical beam. A property of the symmetrical beam is its beam widths in the normal planes remain same, equal. Using that aspect here, it is written theta HP equal to phi HP equal to 2 degrees. Beam area is omega A is equal to theta HP multiplied by phi HP. This is also a relation, a general relation applicable even to dish antennas. So multiplying theta HP, phi HP, we will be getting 1.22 into 10 power minus 3 steradians. Once gamma A beam area is available, directivity can be determined using the relation D equal to 4 pi by omega A. Omega A is available. From this, directivity can be found. In the present case, it is 10.30 into 10 power 3. Now effective aperture is determined. Effective aperture is lambda square over 4 pi into D. Lambda is required. Wavelength is required. This wavelength one can find from given frequency 3 gigahertz. Wavelength corresponding to frequency 3 gigahertz is C by F 3 into 10 power 8 by 3 into 10 power 9.1 meters is the wavelength. So wavelength is available. D is already calculated. So effective aperture can be found without any difficulty. In the present case, it is 8.20 square meter. Now we consider some problems. These problems are on lens antennas. Example 1. A problem on lens antennas. Available power at a 0.3 gigahertz lens antenna terminals is 8 watts. When field intensity in the incoming wave is 10 volts per meter, determine aperture diameter, directivity and beam width. We are asked to find aperture diameter, directivity, beam width. Let us find them. Solution. Effective aperture is related to available power and incident field intensity. That relation is given by this formula. Here AE is effective aperture, WR is available power, S is power density, which is equal to E square by eta. Notice power density is power per unit cross-sectional area. It is given by pointing vector. Usually S is used to denote pointing vector E cross H. In the present case, the wave is a uniform plane wave, TEM wave. Hence E and H are normal to each other. E cross H becomes EH. Not only that, in uniform plane wave, E by H is equal to eta. Therefore, S becomes E square by eta. So S is equal to E square by eta. Hence this relation AE is equal to WR eta by E square. Available power is given as 8 watts. Eta is 120 pi. For free space, E is given as 10 volts per meter. Therefore, effective aperture becomes 30.16 meters square. Assuming an aperture efficiency of 0.6, usually this is the case, 0.6 is considered as a reasonable value in most of the cases for aperture efficiency. Assuming 0.6 aperture efficiency, physical aperture can be found. Physical aperture is effective aperture divided by efficiency 0.6. It gives physical aperture as 50.26 square meters area. Now the dia of the aperture can be found within no time. Physical area is equal to pi d square by 4d is diameter. It gives dia as 8 square meters. So aperture diameter is 8 square meters. Directivity can be calculated using effective aperture. Directivity is 4 pi by lambda square into AE, effective aperture. AE is available, it is 30.16. Lambda is required. Wavelength corresponding to 0.3 gigahertz is 1 meter. 3 into 10 power 8 divided by 0.3 into 10 power 9. It is 1. So lambda is 1. Now D can be found as 379. So directivity is also obtained. Now beam width. From directivity, beam area and beam width can be found. Beam area is omega A is 4 pi by D. 4 pi by 379. In this case, it is 0.033 steradians. From omega A, beam area, beam width can be found. We know omega A is equal to theta HP multiplied by phi HP. As beam is symmetrical, theta HP becomes equal to phi HP. Therefore, theta HP equals to phi HP equals to square root of omega A, aperture area. Omega A is 4 pi by D. Therefore, square root must be here. Square root must be here. Theta HP, phi HP can be found as 0.18 radians. Before going further, theta HP is half power beam width in radians in vertical plane, whereas phi HP is beam width in horizontal plane or azimuthal plane. Another problem, example 2, on lens antennas. A 1.5 GHz lens antenna with a symmetrical radiation pattern is exhibiting half power beam width of 5 degrees. Determine its beam area, directivity, effective aperture, and physical aperture. The given antenna is generating a symmetrical radiation pattern. It implies theta HP is equal to phi HP equal to square root of beam area omega A. Solution. Wavelength corresponding to 1.5 GHz is 0.2 meters and 5 degrees correspond to 0.0873 radians. Beam area omega A is half power beam width square. Actual formula is omega A is equal to theta HP multiplied by phi HP. As pattern is symmetrical, theta HP becomes equal to phi HP. Hence, omega A becomes equal to theta HP whole square or phi HP whole square. So, omega A is a half power beam width square, but it is given that HP BW is 0.0873 radians. Hence, omega A becomes equal to 7.62 into 10 power minus 3 steradians. Now, directivity, effective aperture, physical aperture can be determined. D is 4 pi by omega A. Omega A has already been determined. Beam area is available. Substituting that value in this expression, one can get D as 1650.12 as directivity. Effective aperture can be found from the relation lambda square by 4 pi into D. Wavelength is available, D is available. So effective aperture can be found effortlessly. In the present case, it turns out to be 5.25 meters square. Physical aperture is effective aperture by aperture efficiency. Here, aperture efficiency is assumed to be 0.6. So, physical aperture becomes 8.75 meters square. Another problem, example 3. A 1 GHz lens antenna with an aperture dia of 3 meter is giving unidirectional radiation pattern. Determine its effective aperture, directivity, beam area, beam width. Frequency is given, aperture dia is given. We are asked to find effective aperture, directivity, beam area, beam width. Solution. Wavelength corresponding to 1 GHz is 0.3 meters and aperture radius is 1.5 meter. 3 meters is dia. Hence radius becomes 1.5 meters. Physical aperture area thus becomes pi r square or pi 1.5 square. It should be square meters. Assuming an aperture efficiency of 0.6, effective aperture becomes physical aperture multiplied by aperture efficiency 0.6. Effective aperture requires efficiency, aperture efficiency, which is not given. Hence, we assumed a standard value of 0.6 to compute effective aperture. Now, multiplication gives us effective aperture as 4.25 square meters. Once effective aperture is available, directivity can be determined without any difficulty. D is 4 pi over lambda square into effective aperture. Effective aperture is available, wavelength is available. Now directivity can be found as 592.18. Beam area. Now beam area can be determined from directivity. Beam area is 4 pi over directivity D. D is available. Omega A can be found without any difficulty. In the present case, it is 0.0212 steradian. Beam width. Beam width can be found from beam area using this relation. Half power beam width is square root of omega A. Omega A beam area is available, hence half power beam width can be determined without any difficulty. It is 0.14567 radians in the present case. Another problem, example 4. A dielectric lens of refractive index 1.5 is coated with a matching layer. When it is operated at 10 GHz, find the thickness and index of the layer. Lenses are coated with a matching layer. The purpose of the layer is to prevent reflections into space from the surface of the lens. Presence of reflections leads to inefficient system. Hence reflections are to be eliminated or reduced. Matching layer is used for that purpose. Solution. Wavelength corresponding to 10 GHz is 0.03 meters. Using the given values in the formula, the index and the thickness can be found. The formula for index of the layer is this. NL is equal to square root of N. N is index of the lens medium. NL is index of the layer, whereas N is index of the lens medium. Index is given as 1.5 for the lens. So NL becomes 1.225. Layer thickness is given by the formula lambda over 4NL. NL is available, lambda is already calculated. Substitution gives thickness of the layer as 6.124 millimeters. Another problem, example 5. A 9 GHz dielectric lens with a refractive index of 1.5 is zoned on one of its faces with 5 steps. Determine the step size and reduction in the bandwidth. Also find the thickness and index of matching layer. Basically, we are asked to find step size and reduction in bandwidth. And then we are asked to find thickness of the layer, index of the layer, matching layer. Solution. Given frequency 9 GHz, This one corresponds to a wavelength of 0.033 meters. The step size is related to index and wavelength through this relation. T is step size, thickness of step. N is index. Lambda is wavelength. Thus, step size can be obtained by using the available values for N and lambda. 1.5 minus 1 into T is equal to 0.033. T becomes equal to 6.66 cm. The number of zones N is given as 5. So percentage bandwidth of lens becomes 25 over N percentage. This is percentage bandwidth. N is 5. Therefore, bandwidth is 5%. Matching layer index, it is a square root of N. N is 1.5. Therefore, index of matching layer is 1.22. Matching layer thickness is lambda over 4NL. NL is a square root of 1.5. Lambda is 0.033. So thickness becomes 6.736 mm. Another problem, example 6. An EPMP lens. EPMP stands for E-plane metal plate lens. Operated at 12 GHz has a plate spacing of 3 lambda by 4. This is the spacing. Usually it is indicated by A. Find the wave velocity inside the lens medium. Also find index of refraction of the lens. Simple problem. Provided we have the expressions for phase velocity and index of refraction in our minds. Substituting the given values in the formula for phase velocity can be obtained as Vp is C by square root of 1 minus lambda by 2a whole square. A is 3 lambda by 4. A substitution in this relation gives us phase velocity as 4.05 into 10 power 8 meters per second. Notice this velocity 4.05 into 10 power 8 meters per second is more than free space wave velocity, that is 3 into 10 power 8 meters per second. It can be because this is phase velocity. Phase velocity usually it is more than C, 3 into 10 power 8 meters per second. Group velocity cannot be, but phase velocity can be more than C. The index of refraction can be found from the formula N equal to square root of 1 minus lambda by 2a whole square. Substituting the given value of A, index can be found as 0.745. Another problem, example 7. Find the bandwidth of an EPMP lens when its index N is 0.5. The plate thickness T at the edge is 6 lambda and path difference tolerance delta is 0.25 lambda. Certain data is given and we are asked to find bandwidth and bandwidth when it is zoned with 6 steps. So bandwidth before zoning, bandwidth after zoning. So this problem is essentially about bandwidth of EPMP lens. Solution. Substituting the given values in the formula for bandwidth. Bandwidth B is equal to 200 N over 1 minus N square delta lambda over T lambda percent. This is bandwidth before zoning. N is index, refractive index. It is 0.5. So in the denominator N square is there. So 0.5 square. Delta lambda. Delta lambda is path difference tolerance in wavelengths. It is given as 0.25. So 0.25. T lambda is thickness at the edge in wavelengths. Thickness at the edge is 6 lambda. In wavelengths, it becomes 6. So substituting the given values, bandwidth can be found as 5.55%. This is before zoning. Now we find bandwidth after zoning. Number of zones is given as 6. The bandwidth can be determined from the formula B is equal to 50N by 1 plus Kn. N is index, K is number of zones. Substituting the given values, we get it as 6.25. Before it is 5.55, after it is 6.25. In case of EPMP lenses, bandwidth increases when zoning is performed. We consider some more problems. Examples 8 and 9. These are also on lens antennas. A HPMP lens operated at 10 GHz has a plate spacing of 3 lambda by 4. Find the index of refraction for this lens when the plates are arranged at a slanting angle of 30 degrees. We are asked to find index of refraction. Formula for index of refraction is given here. Zeta, 1 by cos zeta. Zeta is 30 degrees. So giving a value of 30 degrees to zeta, one can determine index of refraction. Another problem, find a dielectric lens antenna. For a dielectric lens antenna, find the tolerance on the thickness and index of refraction for n equal to 1.5 and t equal to 4 lambda. A dielectric lens antenna is there. We are asked to find tolerances on thickness and index of refraction. Two tolerances we are required to find. The dielectric lens has an index of 1.5 and thickness equal to 4 lambda. Solution. Tolerance on thickness is given by this formula, 0.03 lambda naught by n minus 1. N is given as 1.5. Therefore, delta T, tolerance on thickness becomes 0.06 lambda naught. Tolerance on index of refraction is given. Delta n is 3 by T lambda, which is half. You need not consider n here. Delta n is the tolerance on index. It is half percentage. With this, we come to an end of the present session. In this session, we considered several problems on dish antennas and lens antennas. These problems are mainly concerned with directivity or gain, physical aperture, effective aperture, beam area, beam widths, tolerances, etc. Hope this session is useful to you. We meet again in another session soon with a new and interesting topic.